Okay, we're going to start our last unit of the semester, which is on rotation. So when I say last unit, this unit will take us all the way to the end of mechanics, which is the end of the semester. All right. Um, so what you see on the board here are two different types of motion. There is translation and there's rotation. Let me get my camera up here so that I can show you kind of one of the differences between translation and rotation. So let me take this object right here. So say this object was moving, and all the type of motion we've been studying so far, like is translation. So see this object is moving this way, was moving this way, maybe up and down, might be moving in a parabolic projectile motion, maybe moving in uniform circular motion. Okay, these are all translation motion. What makes a translation is like this entire object is moving all together as one unit, right? So like if you imagine the center of this object is moving like this direction, but then this part of the object is moving exactly the same way, right? So this is translation. It's like moving through space, right? Now, when something is translation, let me go back to my other screen. Notice since the entire object is moving all the same way, like up, down, left, right, or maybe parabolic projectile motion or whatever it is, since every part of this object is moving together as one unit, we usually collapse that into a single dot. Like especially, for example, when we're doing like a free body diagram, we just collapse it into one single dot because like since this entire object is all moving together as one unit, you don't actually have to like consider the size or the shape of the object. Okay. So let me contrast that with rotation. Here's rotation. Actually, first let me take this object, but then this would be translation. See, all these motions right here, this is all translation. Okay. But then this would be rotation. All right. And one of the key ideas that makes rotation very different than translation is like different parts of this object are kind of moving differently. So clearly this thing's rotating. I think it's kind of obvious, but like if you imagine, say, this point right here on the outside of the wheel, it's kind of moving, but then this part of the wheel is moving very differently, and then this part of the wheel is moving very differently, right? And then this part of the wheel right in the center is moving very differently, actually not moving at all in this case, right? So this would be rotation. I can use another example. It doesn't have to be a wheel that can rotate. You can have just like a stick right here and say it's rotating like this, right there, right? So this is rotation. This would be translation like this, right? This is translation. This would be rotation, something like that. Notice that with rotation, there's always a rotation point, right? So like, for example, this rotation point would maybe the end of this stick. Like before I was doing the middle of the stick would be the rotation point right here. You can have the end of the stick be the rotation point like that, right? Or you can have any other point be the rotation point. It could be like somewhere just arbitrarily along there, and then it's rotating like that, okay? And then notice once again, what makes this different is that different parts are doing different things. Like this part, the rotation part is not actually moving at all, whereas all these other parts are kind of rotating through space. Okay, so this picture right here, once again, would be rotation. So you can see that dot will represent the rotation point for each of these. Okay. Now, because this object now is rotating about a rotation point, you do actually have to preserve the size and the shape of the object. You can't just reduce this down to a single dot like you could with translational motion. So with rotation, we're always going to consider the entire size of the object. Like what do I mean by that? One example would be like, remember when you do free body diagrams? So all the free body diagrams we had up until now, we'd be like, oh, there's the object, the center dot, and you would have arrows radiating away from that center dot, right? Now, this FBD would be considered a simple FBD, and it still actually has some validity, which I'll talk about like later today. But ultimately, you're also going to do a more complicated FBD, right? That you're going to make a distinction, not just the fact that it's up, down, left, right, or something like that. You're going to draw those forces exactly in the location that those forces act upon, right? Because the location then makes a difference, in terms of its motion from a rotational point of view. All right, so that's one thing we're going to be doing. I will talk about this later when we get to FBDs for rotation. But now you sort of see we have to preserve the size and the shape of the object now instead of just having a single dot. All right. So now you sort of see our objects for rotation are going to be much more complicated. They're not just going to be like single blocks. They'll be like like say like a large block or a rod or a wheel or something along those lines. All right. Now, um, first thing we have to talk about then is kind of let's consider a simple object. All right. Um, Actually, before I talk about that simple object, so then when you're considering the size and shape of the object, all right, I'm going to make a distinction between an object that actually has a size and dimension to it, say like this or like this, right? Versus an object where its mass is concentrated at a single point. Now, this obviously does have a size and a shape in it too, but let's just say that's negligible. And just imagine the mass is all concentrated at a point. That would be a specific type of object called a point mass, all right? And a point mass is the simplest type of object we can imagine. Now, a point mass then can't really rotate because it doesn't really have any dimensions to it, all right? So you can have a single point mass. But imagine like a more complicated object that is actually 2 point masses together as one object. All right. So imagine you had these 2 point masses right here, like there, and they're connected by like some sort of magical string in between them. All right. And then they were connected as one unit somehow, almost like maybe not a string, but if there was like a super thin, very light wire between them, and then this could be like a hanging mobile. I'm not sure if you know what a mobile is. It's like one of those pieces of art that hang from the ceiling and has like 2 pieces on either end, or like multiple pieces hanging from the, from the ends of this like thin rod or something like that. So this might be like an object that consists of 2 point masses at the end. Now I drew those point masses as having a size and a shape, but let's pretend those sizes are negligible. It's actually one mass concentrated in single point with a massless rod in between them and another full mass concentrated at this point. All right. So this would be an object with a size and a shape, but it's actually an object that consists of 2 point masses, are separated by this distance. Okay. Now, the first thing we need to learn about in this unit is something called the center of mass. So every large object has what is called the center of mass. And we'll talk about what the significance of the center mass is later, but let's just actually talk about how you find the center mass first. All right. So let's just say we had 2 point masses right there. Okay. Hopefully it makes sense to you that the center mass of this object will be exactly in the center, right? If those are the same mass, okay? But of course, the next question is, well, what if they weren't the same mass? Hopefully you may be able to think in your heads right now where the center mass is. Well, not going to be in the center, right? But what I want you to sort of think about then, well, which side would it be skewed towards? Would it be skewed towards this side, closer to the light guy, or over here, closer to the more massive guy? And I'm hoping it's kind of obvious, all right? But the next thing I want you to sort of think about is, if I ask you exactly where, what exact location would it be, all right? I'm hoping you guys can sort of think about what would be a likely location exactly where the center mass would be, all right? So hopefully you've thought of that. And if your intuition is kind of telling you maybe like 1/3 of the way along, that intuition would be correct, all right? So like imagine it be like, so if I were to divide this into thirds, that center mass is obviously skewed towards the more massive object, right? But then kind of maybe right there, all right? That's where the center mass would be. Or like, what about this? What if it was M and 3M? Where do you think that center mass would be? Hopefully you guys can already sort of think about where that center mass would be. I'll give you a little bit. And then hopefully you're thinking that maybe like 3/4 of the way would make sense. So like, I'm going to split this into quarters, and then there would be the center mass there, okay? So that intuition is correct. I'm going to show you a formula that allows you to calculate exactly where that center mass is going to be in a more formal way, all right? So rather than just like sort of using your intuition, you have a way of calculating exactly where it would be, all right? So let me show you the first formula for the center mass. This is once again going to be for a collection of point masses, all right? A collection of point masses. Here it is. This formula is actually on your formula sheet, I believe. All right. So, okay. It's going to be the summation of the locations of each point mass times the mass of each point mass divided by the total mass. All right. Let me show you how you use it. If this equation doesn't make sense to you, it will make sense after I show you an example. All right. So let me use this example right here. Say 2 identical masses, point masses, separated by distance L. All right. Now we already know from our intuition the center mass is going to be right here, right in the center. But let me show you how you like officially calculate it using this formula. Okay, so first thing you need to do is set up a reference frame right there. So what I'm defining is like this location right here is 0, and then this is the positive direction. Right? And what this reference frame does is allow me to assign values to like those distances, which those positions, which is what x is supposed to represent. All right. So then, so right there you see that's 0, and that location is obviously going to be L because that distance is L. So then when it comes time to calculate the center mass, you'll do this guy's position times this guy's mass, and then you'll do this guy's position times this guy's mass and add them together, right? So you'll do, for example, for this first guy right here, for this guy right here, you'll do that guy's at location 0 times that guy's mass, right? Plus, and that's what the summation symbol is up there, right? This means to add up every point mass you have. So you're going to do this again for every point mass. So this guy obviously has location L and a mass M, and that's in the numerator. And then you're going to divide this by the total mass, right? The total mass being 2m. And of course, when you simplify that, notice the m's cancel and you get L over 2. And according to our reference frame, L over 2 is right here, which is exactly where you expected the center mass to be. All right, so that's how the formula works. So let's try this again, the exact same scenario, but I want to show that you didn't necessarily need to use this reference frame. You could use any arbitrary reference frame. All right, like for example, same scenario, right? But this time, do you see my reference frame? I'm putting my 0 in the middle, and then that's my reference frame right now, okay? So notice that this location right here, right? Hopefully you can sort of think that that location is not 0 because this is 0 right here. So this location right here is going to be negative 1/2 L, right? And this location here is going to be positive 1/2 L. So then you just have to do those two locations, right? So this first guy is going to be, right, negative 1/2 L times that guy's mass, and then you're going to have positive 1/2 L times that guy's mass, and then you're going to divide it by the total mass again, right? And then notice when you add these together, you're going to get 0, right? Now, of course, so you get a different value than the last one, right, with the other reference frame. So with this reference frame, you got L over 2. With this reference frame, we got 0. But of course, they refer to the actual same physical location in space. It's like exactly in between them, right? So that's why I'm saying it doesn't really matter which reference frame you choose, right? You're going to get the same location if you apply the formula correctly, all right? Like, for example, you could have chosen this reference frame. Like this guy is 0, and this guy is at L, right? Or you could have chosen that 0, then you're referencing this way, and then that guy would have been at negative L, or stuff like that. Heck, you could even choose a random like 0 right here, right? And then, of course, each of them would have an L. Now, its own distance, right, away from 0. I'm not really sure why you do that. You're just overcomplicating things, of course. So clearly, no, this is probably the simplest to make one of them 0, of course. It just makes your math simpler. But the idea is that it doesn't matter what reference frame you choose, you would get the correct location no matter what. So you might as well choose, when yourself, might as well choose the simplest one, okay? All right, so let's try that again for some of the unbalanced ones and see how that works out. So like, for example, let's just say it was M and 2M, all right? So if I use that reference frame, then I'll have this location, 0 times M, plus this location, which is L, but times that guy's mass, which is 2M, right? And then you're going to divide it by the total mass. The total mass, of course, is those two added together, which is 3M. And if you simplify that, you get 2/3 L, which is right there. Right? And then here you'll see some examples of other reference frames right here, right? So this guy's 0, and that guy's L. And notice you get 1/3 L, which of course is literally the same location in space. It's that location right there, right? And then this would be probably one of the not greatest reference frames to use, not very convenient, but it would actually give you the same location too. But I wouldn't recommend you obviously choosing that reference frame. That'd be a little bit difficult. Okay, so that is actually how you use this formula. Once again, this is a formula for point masses, a collection of point masses. All right. So the next level up from that is what happens if you have a two-dimensional object. Like, for example, right here, imagine this is like a two-dimensional collection of 3 point masses. So imagine that mobile again, you're thinking that hanging mobile, it's like 3 point masses connected in 2 dimensions. All right. So instead of just 2 in a line, you have 3 in kind of a triangle orientation like this. All right. And where's the center mass of this? And now hopefully you know that center mass is probably going to be somewhere like in here range, right? Somewhere in the center, in the middle of that triangle, right? Formed by these guys, somewhere in there. Okay. Now, the way you find the center mass is actually pretty easy. Because you have 2 dimensions, you just need to find the center mass for each dimension. So you're going to do that same formula, but you're going to do once for the x dimension and one for the y dimension. Like for example, right, for the x dimension, to find the location along the x-axis for the center mass, you'll do these guys, or like each guy's x location. So you'll do this guy's x location times this mass, this guy's x location times this mass, this guy's x location times this mass, add them all up, divide by the total mass. That'll give you the overall x position for the center mass. Then you'll do the same thing for the y. Like for example, let's do the x. All right. So this guy clearly has 0 x position, so you do 0 times m1. Then you do this guy. Now, of course, this guy's x position is still 0. Oh yeah, by the way, this is all assuming that this is going to be my reference frame axis setup, right? So this guy still has a location of 0x, right? Don't get distracted by this. That's a y location. That will come later for the y position, all right? This guy's x position is definitely 0. So you have 0 times m1 plus 0 times m2. Then you have this guy's lx position times m3, right? And then you divide it by the total mass, which is all 3 of them add together. And this formula will give you the x location of the center mass. And then you just do the same thing for the y direction. Of course, you can sort of hopefully already see that these 2 guys now have the 0 y positions, right? And this guy now has a y position. So it's only m2 that has a y position right here, right? Where the other guys have 0 y position. And then you do the same total mass right there. And then now you have the x coordinate and the y coordinate for the center mass, right? Yeah, so hopefully you sort of see 2 dimensions is not any more difficult than 1 dimension. You just have to do it twice, once for each dimension, okay? All right, I want to give you a quick preview for what you do if your object is not a collection of point masses. So what we call this, these would be like a collection of what are called discrete point masses. Discrete meaning like separate objects that are kind of separated from each other, right? Little point masses that are discrete objects, all right? We do need to talk about, well, what if your object is something like this? Do you notice it's not just single point masses? This is what's called a continuous object, right? It's not separate objects that are all point masses from each other. This is actually a continuous object, all right? So one of the things you will be expected to know how to do is find the center mass of a continuous object like this, all right? Now, I'm going to tell you right now that the techniques to find the center mass of an object like that are actually really quite difficult. It's probably going to be, I would say pretty confidently, this is actually the most difficult technique that you'll learn all year. All right. So it's a technique that you're going to be doing really maybe a little bit more second semester, more than first semester. What I'm going to do right now is introduce this technique without any expectation that you will actually know how to do it by the end of what I talk about. All right. What I'm more just trying to do right now is introduce the idea. All right. And actually, I'm not going to introduce the idea right now. I'll probably might save this, actually for you guys, I might save it for a later day. But I'll just introduce the basic idea rather than the full technique. All right. So the basic idea you're going to do with this is that you're going to, so imagine this was our formula, right? The summation of x's times their masses divided by the over mass. You'll sort of see that this is not quite adequate because what we're going to do is actually like split this guy up into little infinitely small tiny little pieces. All right, say like each piece might be like one little piece, each infinitely small. All right, so it's almost like that continuous object is like a whole series of infinitely small point masses all glued together, right? But all with different positions. Like, so for example, I would have to set up like a reference frame. You see all these different point masses have different positions. And then, so I would actually do like this guy's position times its mass, this guy's position times this guy's mass, this guy's position times this guy's mass, and add them all up. But notice I'm adding them all up in a continuous manner as opposed to like a separate discrete manner. And then hopefully you may know from your calc class, when you add things up in a continuous manner, that's actually called an integral, all right? Kind of the same integral that we've already been doing, right? So really you won't use this. You'll use what's called the integral form of this to add up all of these in a continuous manner. Right? So this is the basic idea. Like I said, the techniques to actually do this are really quite difficult. Right? Super confusing. And I may talk about this at a future date, like how to do this. All right. So for now, let's just use the quick shortcut. Because most continuous objects are kind of obvious. Like for example, see this continuous object right here? Like I'm hoping you can sort of imagine your best guess where the center mass of this object is. I'm assuming your best guess is that it's probably somewhere right exactly in the middle. And you would be correct. All right, so the center of the mass of this object is in the very center of this object. Right? Or like, what if you had a more complicated object that was like this? Okay, well, you could probably imagine that the center mass of this object is exactly right in the center. So if the object is nice and symmetric, then the center of the object is probably going to be the center of mass. All right, and that generally holds true. So that's, you can utilize that. This little right here. The center of the mass, center of mass for symmetric objects is always in the physical center of the object. Right. So you can utilize that shortcut. Very common, actually. All right. In fact, that's going to be the case most of the time for problems at this level of physics. All right. Now, notice this is only true assuming uniform density. So what do I mean by that? Let's say I had a rod right here, but somehow like this part was less dense and it got more and more and more and more dense as you got over here, like it's somehow made out of a different material. All right. Then that means you can sort of see with this center mass would probably be skewed over closer to the heavier side, right? And exactly where it is, that's a very difficult problem to solve, all right? And once again, requiring some pretty advanced calc techniques, which I'll go over it sometime in the future, right? So, but for now, let's just keep it. You can utilize a shortcut for if it's nice and symmetric and it's uniform density, then the center of the object will be the center mass, okay? So now I'm going to talk about then what is the importance of the center of mass, right? The importance of the center mass plays 3 roles. All right. Role number 1 is the location of the force of gravity. All right. What do I mean by that? What I mean by that is the very first step you're going to be doing in any sort of rotation analysis is the exact same step you've always been doing. Draw an FBD. So I'm going to require you to draw an FBD or to do a force analysis. All right. Now, one of the things, though, instead of drawing an FBD like I showed you before, where you have a single dot and points emanating from the dot, you need to somewhat preserve the shape of the object, right? So, but when you preserve the shape of the object, still the very first arrow you can put on there is gravity. Then notice you're going to put that gravity arrow exactly straight down, but this time on the center of the object. All right. So that's the first significance of this. All right. I will teach you guys later how to, build the rest of the FBD. Okay, but this is going to be the first significance of gravity. All right. So that is significance number 1. All right. It's the location of the gravity force. Significance number 2, and just so you know, we'll be utilizing these significance like when we do rotation, over the next few weeks. So it's not like you have to memorize these things all right now. You'll be utilizing all these facts, as we go further into this unit. All right. So I'm just kind of giving you intro with these significances. All right. The next thing is this. The simple FBD tells the acceleration of the center mass. What do I mean by that? Okay. Remember that you can draw the simple FBD and the complicated FBD. What do I mean by that? So this is what you're going to be ending up doing. All right. So like right here on the left, on the right, actually, is a complicated FBD where I'm literally drawing the forces exactly at the location they're supposed to be, right? So like gravity is at the center mass. And notice this normal force is not just going to be anywhere up. It's actually literally going to be at the point of contact, right here. So do you see I preserved the size and the shape of this object? Now, this FBD on the left here still has some validity and still tells you something. What is this FBD? It is just the combination of these two collapsed into like a dot, as if it wasn't a full object. It's just like you're just looking at the forces alone and not their location of these forces. All right. So you have one up and one down. Now, this still tells you something. The simple FBD tells you the acceleration of the center of mass. Right. So you can still set up a force equation Fg minus Fn. So more than likely, this Fg arrow is going to be bigger than Fn. Why? Because that center mass is accelerating downward. All right. So that this sort of setup will tell you, this simple FPD will always tell you what's happened to the center mass. Now, if you want to know what's happened to the rest of the object, you have to look at this thing. All right. Because this may tell you what's happening, like from a rotation point of view. Maybe this thing's spinning as well, or doing all sorts of weird stuff in addition to having the center accelerate downward. All right. But this simple FPD will tell you what's happened to the center mass. Okay. So these first two then are related to your FPD of force analysis. Okay. That's the significance of the center mass. Right. The last significance has to do with an energy analysis. So you might imagine in the future, just like we've been doing with all the mechanics, we have the separation between, you can do force analysis to get acceleration, or you can do an energy analysis, right? And we're eventually going to be doing energy analysis from a rotation point of view. And remember, energy is like KE plus UG plus US plus any work is equal to KE plus UG plus US, that kind of thing like that. And so the only thing that's a little bit different is how you measure UG. Like, what do I mean by that? So like, let's imagine this. Let's just say, like back when we had a point mass, okay, this object is UG. Why? Because it's height off of 0, right? So, and then this would be the height. But what if this object wasn't a point mass? What if this object was actually something like this, right? Like, well, what is this object's height? Like, I mean, there's so many different parts of this object. What part do you keep track of? And the answer is, from a UG perspective, you're keeping track of the center of mass of this object. That's the location of the center mass of the object is what matters from a UG point of view, right? So for example, like right here, the height of this object, well, this height of this object would be kind of obvious because it's all the same height. But say the height of this object, well, it's not the height of that part. It's not the height of that part that matters. It's the height of the center that matters, all right? So when you're going to do MGH, you do, like, if that's your 0, you do mg times this height from here to there, all right? So you can sort of see right here. So like if you had a point mass, you just use the height of the object. But then if you have a more complicated object, you have to use the height of the center mass for the UG. All right. Okay, so those are the 3 significances of the center mass. Like I said, you'll be utilizing this knowledge when we actually go over these topics more specifically, when we do like force analysis and when we do energy analysis. Right. So, right, that is the significance of the center mass. Right. And then so like, for example, oh yeah, actually, like here's an example. Here's another energy example. You can sort of see, like, see this object right here, this ruler falls down, right? And you can sort of see, oh, that it definitely lost height. Like, you're not worried about the bottom of this object that's at the same place. It's the center mass has fallen down, right? So see how the center mass is definitely lower here than it was there. That means in this location is lost UG compared to here, right? But like, here's another example. What if the object was like this? Do you see this object is not losing UG at all, right? Why? Because the center mass isn't changing height in any sort of way. All right, so, okay. So there we have covered center mass and the significance of the center mass. And that will conclude this video. And then it's time to go on to the next video.